In this video, I will review how to write the expression for dissociation of a weak acid or a weak base in water, how to determine the equilibrium dissociation constants Ka and Kb, and the Kw autoionization of water that can help us to determine the concentration of hydronium, hydroxide, pH, and pOH. As discussed in a previous video, in acid-base reactions, equilibria favors proton transfer from a stronger acid to the stronger base to form the weaker acid and weaker base. Commonly, acid or base strength is measured by determining the equilibrium constant of a substance reaction with water. Because the dissociation of a strong acid in water is essentially complete, the reaction is not considered to be an equilibrium process. Weak acids partially dissociate in water as the ion products reach equilibrium with the undissociated weak acid molecules. The reaction of a weak acid with water, like any chemical equilibrium, can be described by an equilibrium equation. The equilibrium constant is called the acid ionization constant Ka. The farther toward the products the equilibrium position is, the stronger the acid or base. The position of equilibrium depends on the strength of the attraction between the base form and the proton. Stronger attraction means stronger base or weaker base. Formic acid, in this example, is a weak acid that dissociates in water to form hydronium ion, H3O+, and formate ion, here highlighted in yellow. As with other dissociation expressions, the molar concentration of the products is divided by the molar concentration of the reactants. And since the change in water concentration is so small, it is neglected. The value of ionization constant for formic acid is 1.8 times 10 to the negative 4, and it has no units. Because it is a small value, that means the majority of formic acid remains intact and a small part has become ionized. Similar to acid dissociation, we also find values for bases dissociation. This equilibrium reaction represents, again, a ratio of products and reactants, ignoring the concentration of water. We see how a weak base like an amine will behave in water, and it is important to recognize that amines are Bronsted-Lowry bases. They are proton acceptors. We rank acids from the most acidic to the least acidic in assessments, and for that we use the Ka values. Greater Kas are stronger the acids. In similar way, we rank the bases from the stronger the base, the larger the Kb. You have seen plenty of equilibrium expressions, nothing but the ratio between the concentration of the products versus the concentration of reactants. Of course, a reminder, we ignore the change in concentration of water because its change is too small to make a difference. Acid strength is measured by the size of the equilibrium constant when it reacts with water, Ka. Nature is rich in carbonyl compounds, that is, when you have a carbon-oxygen double bond, and carboxylic acids belong to these families. Most organic acids will have a COOH that has a Ka value near to 10 to the negative 5. In this we have, for example, acetic acid that is found in vinegar and propanoic acid. You will find tables with those values, those Kas and Kb, and in assessments they will be provided. You do not need to memorize any of those Ka or Kbs. Water is an extremely weak electrolyte. Therefore, there must be a few ions present. About 1 out of every 10 million water molecules form ions through a process called the self-ionization or auto-ionization. All aqueous solutions of water contain both hydronium H3O+ and hydroxide OH-. The concentration of hydronium and hydroxide are equal in pure water. That is, they are equal to 10 to the negative 7 molar at 25 Celsius. The ion product constant for water, Kw, is defined as the product of the concentration of hydronium and the concentration of hydroxide, and it is equal to 1.010 to the negative 14 at 25 Celsius. The concentration units are omitted. The product of the concentration of hydronium and hydroxide are always the same. You multiply those two concentrations, it will always give you the same value of 1.010 to the negative 14. The number is called the ion product of water equilibrium constant and it has the symbol of Kw. If you measure the concentration of one, you know the concentration of the other. When the concentration of hydronium increases, that of the concentration of hydroxide must decrease, so the product stays the same. They are inversely proportional. All aqueous solutions contain both hydronium and hydroxide. Neutral solutions have equal concentration of hydronium and concentration of hydroxide, and they are both equal to 1/10 to the negative 7. Acidic solutions have larger concentration of hydronium than concentration of hydroxide. Basic solutions have larger concentration of hydroxide than concentration of hydronium. Like all weak acids, water is slightly dissociated into H plus and OH minus, or let's say hydronium and hydroxide. The ion product constant for water is again 1.0010 to the negative 14 at 25 Celsius. In pure water, the ionization of water molecules produces small but equal quantities of hydroxide and hydronium. If we know the concentration of hydronium of a solution, we can use the Kw to calculate the concentration of the hydroxide ions. The acidity or basicity of a solution is often expressed as a pH. pH is minus the log of the concentration of hydronium, and the concentration of hydronium is 10 to the negative pH. The pH of pure water is minus the log of its concentration, which is 10 to the negative 7, which is 7. That is a neutral pH. pH lower than 7 is acidic, pH greater than 7 is basic, and pH equal to 7 is neutral. The pH of a solution is used to indicate the acidity of a solution. The pH has values that usually range from 0 to 14. A pH is acidic when the values are less than 7. A pH is neutral when the pH is 7. And a pH is basic when the values are greater than 7. How can we relate pH and pOH? If we know the value of Kw, we can get to the value of pOH by using the pH. Kw is equal to the product of the concentration of hydronium times the concentration of OH. If the only information available is the pH, the easiest way to get the pOH is by using the log of Kw, and we get that pH plus pOH is equal to 14. What brings us to the pH scale from 0 to 14, what can be measured. So pOH is equal to 14 minus pH. In this example, the concentration of hydroxide is known. We solve for concentration of hydronium. Kw divided by the concentration of hydroxide gives us the concentration of hydronium, which is equal to 2 by 10 to the negative 7. Since its value is greater than that for the concentration of hydroxide, this solution is acidic. In this example, the concentration of hydronium is known. We use the same formula, but this time we divide the ionization constant of water, Kw, by the concentration of hydronium. The concentration of hydroxide is really small, it's 10 to the negative 12. This solution is acidic. We know that because the exponential for concentration of hydronium is lower than negative 7. Let's calculate some pHs. Now with the two previous concentrations, concentration of hydronium and concentration of OH, we can calculate the pHs. We said the pH of hydronium is minus the log of its concentration is 2.7, is acidic. And when we calculate the pOH is acidic because it has a high value. When we add those two numbers, we know that they will add to 14. Now we have arrived to the pH scale and some important some substances that we use with the pHs where they are. But the pH scale goes from 0 to 14, and we can see here that you need to be very careful when you are handling the battery of your car or cleaning supplies, because so we know that sulfuric acid has a pH of 0 and Drano has a pH of 14. Be careful with that. Is there a pH that is lower than 0? Yes, there is.